In this lecture, we will be learning about exponential functions. So first, the definition. An exponential function is a function of the form f of x equals a to the x, where a is some positive real number, called the base. So it's a constant raised to a power. So a constant raised to a variable power. And we know how to make sense of this. If we look at different cases, if n is a natural number, so n is a counting number, then a to the n is just a times a times a, right? There's n copies of a in the product. If n is, say, an integer and it's negative, then a to the n is 1 over a to the minus n. Right? If a is negative, then, if n is negative, then negative n is positive, and this becomes 1 over a times a. Right? Again, n terms. If n, why don't we say, instead of n, why don't we say r? If we have a rational power, so remember, boldface Q stands for the set of rational numbers, then it can be written as a ratio of two integers. So P and Q are elements of the integers. And in that case, a to the r is a to the p over q, which we're used to doing, where you would say this is the qth root of a to the p, or the qth root of a raised to the p. So these are all ideas that we're used to. Now, one thing that we're not used to is the case where, so we have these three cases so far, but if we have just a real number r, but suppose r is not an element of the rationals. So this is the case where r is irrational. And that's a new idea. Because what does it mean to say have 2 to the pi? Because you can't write pi as a ratio because it's irrational. You can't use this approach. But what we do is we say, in this case, a to the r will be the limit as x approaches r of a to the x, where x is restricted to the rational numbers. And so the idea here is it's because the rationals are what we call dense in the real numbers. So we can find rationals arbitrarily close to this irrational number r. And that limit of a to the x, as we have rational numbers approaching that r, gives us what a to the r will be when r is irrational. We need that because if we want to think of these functions as being continuous, we need to have them defined for any real number x, not just the rationals. We also need the irrationals. So because of this, we can fill in what the graph will look like So if we want to look at the graph of y equals a to the x, first of all, they will always have a y-intercept of 1 because a to the 0 is 1. We know that from our exponential rules, which we'll actually summarize on the next slide. And why don't we do, well, I guess we can just kind of draw the general picture. As long as a is bigger than 1, we have something growing like this, and then it asymptotically approaches the x-axis as x goes to negative infinity. This is what a general exponential function will look like. If a is between 0 and 1, we reverse the picture. We still have that y-intercept of 1, but now we're going this way. Let's look at a concrete example. Let's look at the example of, well, actually, before we look at that example, let's just summarize this. These are rules that we've already learned before calculus for exponentials, and they all hold in the same framework. So a to the r plus s is a to the r times a to the s. A to the r raised to the s power is a to the r times s. A to the minus r is 1 over a to the r. And then if we have ab raised to the r, we can distribute that power of r. And a to the 0 is 1 for any a greater than 0. Again, these are rules that you will already know from your previous studies. And they still hold in this situation now that we have a continuous function a to the x. The example we want to look at is 2 to the x. And this is something that we're fairly used to for, say, integer powers. So we can just put some points on here. First of all, we remember 2 to the 0 is 1. 2 raised to the first power is 2. 2 squared is 4. Two cubed, we're already off the picture, we're barely there. So 3 cubed is 9. And so we continuously connect these dots. If we go the other way, 2 to the minus 1 is 1/2. 2 to the minus 2 is 1/4, even lower. And 2 to the minus 3 is 1/8. And you can see how we're really getting 2 to the minus 4 is 1/16. And you can see how we're getting very close. We're honing in on the negative x-axis as x goes to minus infinity. And then the way that we're defined at the rationals fills in all the points on the graph at the rational numbers, and then our limiting rule for irrational values of x completely fills in the graph, and we get a continuous function. So it makes sense to be able to do things like 2 to the pi. We know pi is 3.14, so pi is somewhere in here, and we can get 2 to the pi just by going up and finding it on the graph. So we now have this exponential function that is continuous in x. Prior to having the idea of a limit, we didn't have that, because we didn't have a rule for this idea of a raised to a irrational power, because that power couldn't be written as a ratio. Now with this idea of limit, we do. So this thing is a continuous function defined for all x. Its domain is the whole real line. That being said, as students of calculus, if we have a continuous function, the natural question is it differentiable? And the answer is that it will be. And we have a very special case here with exponentials. So let's actually compute the derivative of a general exponential function. So recall, as usual, we always start with our definition for a derivative. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, our f of x is this a to the x. So we first do a to the x plus h. Then f of x is just a to the x. So minus a to the x all over h. Well, we should be careful. We want to remember our limit expression. There we go. Let's use our rules for exponents to break this up as a to the x times a to the h. And now we note that we have an a to the x term common in both numerator terms, which means we can factor that out. So that leaves us with a to the h minus 1 over h all times a to the x. So this is our derivative. What's interesting is that this term here, notice that that does not contain x. What that means is this limit, if we are factoring this a to the x out, right, a to the x has no h, so you can think of factoring it out of the limit. And maybe that's a good thing to do explicitly. So what we have is a to the x times the limit as h goes to 0 of the quantity a to the h minus 1 over h. So we now see that this derivative, f prime of x, equals a to the x, which is f of x, the original f of x, times this limit. This is just some number. There's no x involved here. It's a number, right? H is going to 0. That's the limiting factor. But it's a number that depends on a. So this is some number depending on a. And that's an important thing to recognize, that there's no x in there, which means this limit is just a number. So let's give it a name. We'll call it m of a. So what that means, summing this up, if f of x is a to the x, and remember, a is just some fixed number that's greater than 0, our base, given that function, its derivative, f prime of x, is equal to some number, we call it m of a. So some number that depends on a, times the original function, a of x. Summarized here. So the derivative of the function a to the x is some number that depends on a times a to the x. And our question is then, what is m of a? And if we start experimenting, so let's think about what these axes are. These are different bases. So for different bases, what's that m of a? What's that scaling factor? And if you start trying some numbers, if you plug in 2, you get about 0.69. If you plug in 3, you get something above 1, and the key number here is 1. That's what we're interested in. So if the derivative of a to the x with respect to x is some number times the original a to the x, a really cool situation is, what's the a where this is 1? So what a has this property? If this is equal to 1, then this would be a function whose derivative is itself. And it turns out that with our graph here, we have a continuous function here, m of a, which we'll talk about later in the course. We haven't defined it yet. But by the intermediate value theorem, there's going to be some x in this interval 2, 3 where this actually holds. And that number has a very special name, and we call it e. E is approximately 2.71828, but it's irrational. So it's a non-repeating, never-ending decimal, cannot be written as the ratio of two integers. So when our base is e, so this e here if we call this equation star, star becomes the derivative of e to the x with respect to x is 1 times e to the x. And this is a very important function. We name it the natural exponential function. It's the only exponential function whose derivative is itself. And in fact, that's going to be true. Aside from multiplying by a constant, it's the only non-trivial function whose derivative is itself. When I say non-trivial, think like the function f of x equals 0 has derivative that is itself. But it's going to be the special function that has this property. Its derivative is itself. And we define it formally here on the next slide. Our natural exponential function. So this is what a summary, formal summary of what we just went over on the previous slide, but it is the exponential function such that its derivative is itself. The graph of this function looks a lot like the graph of 2 to the x that we had just drawn. We have our y-intercept of 1. It asymptotically approaches 0 as x goes to minus infinity. But the neat thing is, if you think about what this means, at any given point, and I should draw this a little more carefully. But at any given x, the slope of the tangent line is given by the function value. So for example, here at x equals 1, sorry, at x equals 0, the slope of this tangent line at x equals 0 is, if we call e to the x f of x, f prime of 0, but that's also e to the 0, or 1. So we see that this tangent line has a slope of 1. If you went to another point on this line, suppose we were at x equals 2, and we look at the tangent line here, so the tangent line at x equals 2, its slope is f prime of 2, or e squared. And what's neat is that's actually also the y value. So the value of the function at any point is also the slope of the tangent line to the function at that point. This is what graphically it means for this derivative of e to the x to be itself e to the x. This function comes up in many different contexts in calculus and in applications. This is a very, very common function. But let's look at some examples now that we have these differentiation rules. So here we have a chain rule problem. So our derivative, and it might be a little bit easier to name the intermediate variable. We have u equals x cubed, and then y equals e to the u. So our chain rule says, so if this is, we say y is g of x. G prime of x, which is dy dx, is dy du times du dx. Now dy du, looking at this here, from the rules we just developed, we know dy du is e to the u. That's this very special property of the natural exponential. And then du dx from power rule is 3x squared. So putting these two together, g prime of x, which is dy dx, is dy du, which is e to the u, times du dx, which is 3x squared. Substituting back in for u gives us e to the x cubed times 3x squared. Now, when we did this, we wrote out explicitly the intermediate variable u, so we could formally show how we use chain rule. It's fine to go from this answer, or from this g of x, straight to this step. The way that you would do that is say the derivative of the outer function, leaving the inner function alone, e raised to a variable, differentiate with respect to that variable, we get e to that variable. But then we multiply by the derivative of that, which is 3x squared. When people see this for the first time, it can be a little bit deceiving because the idea that the derivative of e to the u with respect to u is just e to the u can be one of those things that it's very simple, so it's deceiving. But this is the idea. If we look at the other example, here we have a product rule question. So for product rule, we have the first times the derivative of the second. Well, the derivative of e to the x with respect to x is e to the x. Plus the second, e to the x times the derivative of the first, which is 2x. And if we like, we can factor out the e to the x. E to the x times quantity x squared plus 2x. If we look at another example, y equals minus e to the x, in this case, dy dx is derivative of the outer function, leaving the inner function alone, times the derivative of the inner function, derivative of what's in the exponent, which is minus 1. So we would get minus e to the minus x. This is a function, essentially, think of it as e to the minus x. You're essentially flipping the x-axis. So what you get is your e to the x graph, except mirror image about the y-axis. And these functions come up in a lot of applications. You'll see the application I'm going to mention now in the next calculus class when you do integral calculus. But when you do things like exponential decay, half-life questions, you see this. And then when you do questions that deal with exponential growth, you see these types of exponential functions coming into play in application. It's also the case that we have an important theorem. Now, this is a theorem that we can actually prove once we learn a rule when we deal with something called an indeterminate form, and we learn the rule of L'Hopital's rule. But this is a interesting limiting theorem for e to the x. So notice n goes to infinity. You have n in the denominator and in the exponent. And this, as n gets larger and larger, this expression is getting closer and closer to e to the x. One way that this comes up often is in finance. So for example, if R is an annual interest rate, compounded monthly, think of that like if you get 5% a year, at the end of the first month in your savings account, the bank will deposit 1/12 of 5% of your balance. At the end of the second month, they'll do it again. So what's happening is, at the end of 1 year, just as an example, or why don't we say at the end of an n-month period, your balance, your bank balance, is, so we'll say it's a function of how many months you had. And so we'll call it B naught. That's your initial deposit. So think of this as a bank account that you put money in and then you just left it. Well, at the end of the first month, you're going to get, why don't we make this a little bit simpler and say, why don't we say we're doing a 12-month period to make this simpler. So we have a 12-month period. At the end of that 12 months, how much money do we have? Well, we have at the end of the first month, we got a 1/12 of our annual interest on that amount. So think of it simple. If R was 12%, this would be 1 plus 1%. So the 1, we keep our initial balance, and then we get 1% of it. Well, at the end of the next month, we get another interest payment. And we're making interest on our interest. We call this compound interest. And we do this until the end of that year, where we get our last payment. So we would have 12 of these terms. So this can be rewritten as B0 times 1 plus R over 12 to the 12. And the reason I give this example is notice that this 12 in the denominator of this interest term and this 12 in the exponent match. Well, what if you had more frequent interest compounding? What if you had it every week? Well, there's 52 weeks in the year. So at the end of the 1 year, you would have, each one of these terms would be R over 52, but you'd have 52 of them. What if you did daily compounding? Well, then you'd have R over 365, but you'd have 365 terms here. So you'd have a 365 in the numerator. Well, what if you did it every second? However many seconds you have in a year, that's how many terms you would have, and that would be your denominator in each one of these terms. So the idea there is if you compounded more and more frequently, every second, every microsecond, every nanosecond, what's happening is you would be moving towards, so more frequent compounding say letting this term here, that's our n, approach infinity, we get the bank account balance, we'll say after 1 year, as being the limit as n goes to infinity of 1 plus that r over n to the n, which is e to the r. And we would call this interest rate a continuously compounded interest rate. So the idea is your interest is compounding continuously in time. And the way to think of that is, if you logged into your bank account right now, you would see a balance. But if you logged into it, pi over 3 minutes in the future, you'd see a slightly higher balance because you're continuously compounding in time. And so this idea of continuously compounded interest and this continuous compounded interest rate is really fundamental in the field of finance and mathematical finance. So kind of a neat thing to see in terms of exponential functions. And again, we need a little bit more math. We need to handle indeterminate forms to actually prove this theorem. But this is a pretty widespread application of exponential functions.